Have you ever wondered what it would sound like if two of the universe's most massive monsters collided? Not with our ears, of course, but through the very fabric of space and time itself. On November 23, 2023, three incredibly sensitive instruments scattered across our planet detected something that shouldn't exist according to our current understanding of the universe. They heard the cosmic scream of two black holes so massive that their very existence challenges everything we thought we knew about how these cosmic titans form. Today, we're diving into the most massive black hole merger ever detected, an event so extreme it's literally bending the rules of physics. This isn't just another space discovery. This is a window into events so violent they make our sun's nuclear furnace look like a candle flame. We're talking about black holes weighing 140 times more than our sun, spiraling together in a cosmic death dance that ended with a collision releasing more energy than all the stars in the observable universe combined. If you're enjoying this journey through the extremes of physics, go ahead and give it a like. It really helps us bring you more mind-bending space content. Let's start with what actually happened out there in the cosmic deep. Picture two regions of space where gravity has become so intense that not even light can escape. That's what we call black holes. But these weren't your garden variety black holes. The first one weighed in at 100 times the mass of our sun. To put that in perspective, imagine cramming 100 suns into a sphere about 370 miles across, roughly the distance from Los Angeles to San Francisco. The second black hole was even more massive at 140 solar masses, compressed into a similar mind-bogglingly small space. Now here's where things get really wild. These two cosmic monsters weren't just sitting still. They were locked in an orbital dance, circling each other faster and faster as they drew closer together. Einstein predicted over a century ago that such massive objects accelerating through space would create ripples in the very fabric of space-time itself, gravitational waves. Think of it like two bowling balls circling each other on a stretched rubber sheet, creating waves that spread outward as they spiral inward. But wait. There's something deeply troubling about these numbers. According to our best models of how stars live and die, black holes this massive shouldn't exist. When massive stars collapse at the end of their lives, there's a theoretical limit to how big the resulting black hole can be. Stars massive enough to create black holes over about 65 solar masses should explode so violently that they blow themselves completely apart, leaving nothing behind, no black hole at all. This is called the pair instability supernova, and it creates what scientists call the black hole mass gap. So how did these forbidden giants come to exist? One possibility is absolutely mind-blowing. These massive black holes might themselves be the products of earlier mergers. Imagine smaller black holes colliding and merging over billions of years, growing larger with each cosmic meal. It's like a cosmic version of that old video game where you absorb smaller objects to grow bigger, except the stakes are measured in solar masses and the playing field is the entire universe. You know what's even crazier? These black holes weren't just massive, they were spinning. And not just spinning a little bit, at least one of them was rotating at nearly the maximum speed allowed by Einstein's theory of relativity. Imagine a sphere 370 miles across, spinning so fast that its equator is moving at a significant fraction of the speed of light. The laws of physics literally won't allow it to spin any faster without tearing the very fabric of space-time. When these two titans finally collided after millions of years of spiraling together, the violence of the event defies human comprehension. In the final milliseconds, they were orbiting each other hundreds of times per second, distorting space and time around them into pretzel-like configurations. Then, in an instant lasting less than a tenth of a second, they merged into a single black hole with a mass of 225 times our sun. But wait, if you do the math, something doesn't add up, does it? We started with 100 plus 140, which equals 240 solar masses. But the final black hole only weighs 225 solar masses. Where did those missing 15 suns worth of mass go? This is where Einstein's famous equation, EMC quadred, comes into play. That missing mass was converted directly into pure energy in the form of gravitational waves, ripples in space-time that traveled for over 1 billion years before washing over Earth. Empathetic, it's humbling to think about the scale of these events. While we go about our daily lives, making coffee, stuck in traffic, worrying about deadlines, out there in the cosmos, events of unimaginable violence are reshaping the universe. These gravitational waves pass through you, through me, through everyone and everything on Earth. For a brief moment, we were all stretched and squeezed by an infinitesimal amount as space itself rippled like a pond disturbed by a thrown stone. The detection of this merger, labeled GW23121, was made possible by one of humanity's most ambitious scientific endeavors, the LIGO-Virgo-Cagra collaboration. Picture laser beams traveling down vacuum tubes several miles long, so sensitive they can detect changes in distance smaller than a proton's width. That's like measuring the distance to the nearest star and detecting if it moved by the width of a human hair. LIGO consists of two enormous L-shaped detectors, one in Louisiana and one in Washington state. Each arm of these detectors stretches 2.5 miles. Imagine driving for 5 minutes at highway speeds just to go from one end to the other. Virgo, located in Italy, adds another perspective, while Cagra in Japan brings its unique underground location that shields it from surface vibrations. Together, these instruments form a planet-wide ear listening for the whispers of the cosmos. But how do we know these signals are real and not just noise from trucks driving by or earthquakes on the other side of the world? This is where having multiple detectors becomes crucial. Gravitational waves travel at the speed of light, so they hit each detector at slightly different times. By comparing the exact timing and pattern of the signals, scientists can triangulate where in the sky the merger occurred and confirm it's not just local noise. The sheer extremity of GW2312123 pushed these incredible instruments to their absolute limits. The signal was so strong and complex that our current computer models struggled to fully analyze it. Dr. Sophie Beanie from Caltech described it as pushing our instrumentation and data analysis capabilities to the edge of what's currently possible. Imagine trying to reconstruct a symphony from the vibrations felt through the floor. That's the level of challenge these scientists face. Empathetic, what strikes me most about this discovery is how it reveals both the power and limits of human understanding. Here we are, barely evolved apes on a tiny rock, detecting collisions between objects so massive they warp the very fabric of reality. Yet at the same time, these discoveries show us how much we still don't know. Our best theories said these black holes shouldn't exist, yet there they are, defying our models with their very presence. What other cosmic rule breakers are out there waiting to be discovered? Since 2015, when LIGO made the first ever detection of gravitational waves, we've found over 300 black hole mergers. Over 200 of these were detected just in the most recent observing run. Each one tells a story billions of years in the making, a tale of stellar death and gravitational violence that reshapes our understanding of the universe. The rapid spin of these black holes adds another layer of mystery. Black holes can spin because they inherit the rotation of the matter that formed them, like how a figure skater spins faster as they pull their arms in. But spinning at nearly the maximum rate allowed by physics, that suggests these objects have a complex history, perhaps gaining their spin through multiple mergers or by feeding on surrounding matter in very specific ways. You know what's wild? The energy released in gravitational waves from this single merger was more than all the light from all the stars in the visible universe combined. Yet these waves are so weak by the time they reach Earth that detecting them requires measuring distances to a precision of 1/10,000th the width of a proton. It's like hearing a whisper from across the universe. There's something deeply poetic about gravitational wave astronomy. Unlike light, which can be blocked by dust or distorted by gravity, gravitational waves pass through everything unchanged. They carry pure information about their source across billions of years, delivering messages from a time when Earth was a lifeless rock and complex life was still billions of years in the future. Interested Dr. Charlie Hoy from the University of Portsmouth pointed out that the extreme spin of these black holes makes the signal difficult to model and interpret. In science speak, that's basically saying we're not entirely sure what we're looking at, but it's amazing. This uncertainty isn't a weakness, it's the driving force of discovery. Every mystery solved reveals new questions, pushing us to develop better theories and more sensitive instruments. What will we discover when the next generation of gravitational wave detectors comes online? Plans are already underway for instruments that will be 10 times more sensitive than current detectors. These future observatories might detect black hole mergers from the very early universe, perhaps even catching the birth cries of the first black holes to form after the Big Bang. The story of GW231123 reminds us that we live in an age of cosmic discovery. Just as our ancestors looked up at the night sky and wondered what those points of light were, we now listen to the universe with instruments of extraordinary sensitivity. Each detection brings new puzzles, black holes that shouldn't exist, spins that push the boundaries of physics, and hints of formation mechanisms we're only beginning to understand. But perhaps the most profound aspect of this discovery is what it says about us. Here we are, collections of atoms forged in the hearts of dying stars, building machines precise enough to detect the death throes of objects millions of times more massive than the stellar furnaces that created us. Every gravitational wave detection is a triumph of human curiosity, cooperation, and ingenuity. Dr. Mark Hannum from Cardiff University called this discovery a real challenge to our understanding of black hole formation. In science, such challenges are gold. They're the cracks in our current theories where new understanding can grow. Perhaps these massive black holes are telling us something fundamental about the early universe, about how the first stars formed and died, or about physics we haven't yet discovered. As we stand on the shore of this new ocean of gravitational wave astronomy, what other surprises await us? Will we detect the collisions of neutron stars that forge the heavy elements in our jewelry? The spiral of black holes around supermassive giants at the centers of galaxies, or something completely unexpected that revolutionizes our understanding of the cosmos? The detection of GW 231123 is more than just another scientific measurement. It's a reminder that we live in a universe far stranger and more wonderful than our ancestors could have imagined. From the human perspective, these discoveries connect us to something larger than ourselves. They remind us that we're part of a cosmic story billions of years in the making. So the next time you look up at the night sky, remember that it's alive with invisible violence and beauty. Black holes are merging, neutron stars are colliding, and the very fabric of space is ringing like a cosmic bell. And here on Earth, scientists are listening with instruments so sensitive they can hear the universe sing. What do you think these forbidden black holes are trying to tell us? Are they remnants of an earlier, more violent universe? Products of exotic physics we haven't discovered yet? Share your thoughts in the comments below. I love hearing different perspectives on these cosmic mysteries. Thanks for joining me on this journey to the extreme edges of physics and human understanding. These discoveries remind us that there's always more to learn, always new frontiers to explore. If you enjoyed diving into the depths of space-time with me today, hit that subscribe button for more adventures at the boundaries of human knowledge. Until next time, keep looking up and wondering what other impossible things the universe has waiting for us to discover.